Xiaozhou is going to present the Celer Network, which is really exciting. So, yep, take it away.
Hi, yeah, it's a great talk of speed murmur. And now I'm Xiaozhou Li from Celer Network. I'm here to try to offer you a new perspective of off-chain payment network routing. So, yeah. So before going to the details of the payment network routing, I want to quickly have a high-level overview of the Celer Network architecture. So at Celer Network, we want to build an internet-scale, trust-free, and privacy-preserving platform where everyone can quickly build, operate, and use highly scalable decentralized applications. Most of our team members are based in San Francisco areas. That's why I'm now feeling my jet lag. Yeah, Celer Network is not a standalone blockchain. It's a networked system building on top of existing and future blockchains that support smart contract logics. So it's basically a layer between the underlying blockchain and the massively scaled decentralized applications running on top of it. So at the core of Celer Network, we have three components, three layers, the underlying C channel, and on top of us, the cRoute, and the COS. In the next few slides, I'll quickly go over a review of these components. So the bottom layer is C channel. It's a generalized state channel and a sidechain suite that form the cornerstone of the off-chain scaling platforms. So what we mean by generalized state channels is that it can support generic, actually arbitrary off-chain state transitions. Because we believe that blockchain is much bigger than just payments. By supporting these generic off-chain state transactions, we are possible to support a large variety of decentralized applications, such as generic conditional payment, multi-party gaming, second price auctions, high-frequency exchange, and etc. And more importantly, we think that we propose the concept of the pure off-chain contract. So when talk about the generalized some off-chain computation, maybe many people have the mental model that for the life cycle of the off-chain computation needs three phases. The first on-chain setup, and then off-chain computation, then possible on-chain resolution. But actually, this mental model is not that correct, because we don't actually need this on-chain initialization for every off-chain contracts. We only need this on-chain initialization for payment-related stuff, or actually because we need deposit some values on-chain to prevent double spending, basically to prevent some risk condition of a common state that need to be accessed by any other users in the blockchain. But suppose, let's say, two parties play a chess game, and with some bets that the loser pays the winner $10. So this conditional payment stuff, if these two parties already can reach each other through the generalized state channel network, this chess game does not need to be initialized at all. They can just start with this pure off-chain contract and only need to deploy this contract if someone do not cooperate, if someone want to trigger a dispute. This way, we can make the off-chain platform highly efficient. So there are similar projects, also very exciting and inspiring, working on the similar scope, counterfactual, for example. And we share the same great goal here with some differences in some technical details. And on top of this networked state channel, we have cRoute. It's a highly efficient payment network routing. There's a bunch of net properties of optimal throughput, transparent channel balancing, decentralized failure resistance, and privacy preserving. I'll defer to the detailed discussion to later of the talk. And remember, previously I talked about this two-party player chess game. So building such off-chain application is not that as easy as building an on-chain application. Because any on-chain application just like a front end with some smart contract associated. But to build an off-chain application, it could be much more complicated. That's why we propose COS, which is the development framework and a runtime for decentralized applications that can be scaled through off-chain scaling techniques. So our COS provides like the common design patterns so that people can quickly build their applications and let the COS hide the additional complexities. And we want to enable like a write once, run anywhere property. For example, can we just write the chess game in Solidity and also run it in the off-chain communications? And the COS needs to figure out the dependency DAG between the arbitrary states and track and dispute off-chain states and support concurrent off-chain DFs. Okay, now let's talk about payment. So payment, I don't think we need a motivation here for off-chain payment. So everyone already have like a very good concept of what a payment network is. Basically, we have a payment channel, and now let's for simplicity, we just assume like bi-party channels, and X and Y connected by a payment channel. Each of them has some balance, and a payment is actually just a balance transfer. And the only requirement is that each balance cannot go below 0. So if you only look at this network graph, you may think that it is very similar to like the traditional data network problems we have been studied for decades. So like the existing like payment routing proposals are all based on variants of distributed shortest path routing, like some landmark-based routing, embedded-based routing, but they are all essentially come down to distributed shortest paths. But however, we want to propose a new view of this payment network routing. Because this payment network routing, though looks similar to traditional data network routing, they actually have fundamental difference. For example, here we have like a two-link model of the data network and payment network. A data network is just two nodes connected by a link with some bandwidth. They actually have very nice and simple properties. They are stateless, right? Their status are not affected by data transmissions. What does it mean? It means that its max rate is always fixed. For example, these two nodes have a 1 gig link. It means that it can transfer 1 gig data per second. It can always transfer 1 gig data per second, no matter what did you do in the past. And it can never transmit 2 gig data per second. So it's resulting in a stable network. However, for a payment network, the link is fundamentally different. It is stable. Every single payment changes the payment status because it changes the balance. So the maximum rate, if you think about how many payments can transfer between these two parties, the maximum rate can range from 0 to infinity. Of course, it's not exactly infinity, but it means that if two nodes just keep sending each other $1, the rate is only bounded by the physical computation, whatever. It's nothing related to the balance to the deposit. Which means the network is constantly changing. Again, every value transfer changes the network. So this is a completely new link model. So what does it mean? It means there are some serious problems with distributed shortest path routing. First, it does not account for channel balance. Especially, it does not account for the channel balance change associated with each transfer. And actually, all the distributed shortest path routing share the same basic assumption, is that the network is relatively stable. Of course, there are links comes and go, but still, it's in the low frequency. Whenever the network changes, it needs to take time to reconverge. For distributed routing algorithm, this reconverge actually takes time. And this is like the million-dollar or billion-dollar questions like Cisco, Arista, these traditional networking companies are solving, how to make this reconvergence time, how to minimize this reconvergence time. But it's a very hard problem. And for payment networks, as I've already talked about, it is extremely dynamic, so that the network would be hard or never converge. Because every payment, as I said, every payment will change the network, and then if you are trying to start a converge, it takes some time. When it will converge to another state, the current network states may already change to another phase. Let's take a quick example of the problem. For example, we have this very simple network. It's just a 3-node full mesh. A pays B, B constantly pays C, C pays A. And initially, each node has 100 bucks balance to the other nodes. And the routing path, the shortest routing path is just trivial. And after some while, because of the payment is going on, and the balance from one direction will become 0. And now, in time slot 2, the shortest path to each node now change to this direction. And in another time slot, because now nodes start to send through this counterclockwise direction, the balance becomes 0 in the other way, and the shortest path routing changes again. But because these are all desynchronized, and the convergence time may be very long. Observing the issues above, so in Celer Network, we propose cRoute. So it's a new routing mechanisms, and we have 3 layers. The first is the most fundamental layer, the forwarding layer, like how to deal with the challenges I just described. We call it a distributed balanced routing layer. And on top of that, we have the policy layer. It enables flexible policy configuration and enforcement, something similar like BGP. You can enforce routing, the high-level routing policy flexibly. And then on top of that, we have an optional overlay layer that use onion routing to enable privacy-preserving properties. In this talk, I'll mainly focus on the forwarding layer, how the distributed balanced routing. So the distributed balanced routing mechanisms in Celer Network is inspired by the backpressure routing from wireless mobile ad hoc network. So it is actually a very mature and a very well-studied techniques in the wireless mobile community. It is not used in the wire data networks because it requires like a per packet computation processing, which is infeasible in like high-speed switches. But we found that it is very suitable for payment networks. So the design philosophy of the distributed balanced routing is that it is completely different actually from existing solutions, because there is no explicit path computation from source to destination. So the value is just dynamically routed through congestion gradients and channel balances. There are 2 principles of our DBR routing. The first is follow the congestion gradients, so that the nodes, each node will route the payments in directions that maximize the differential backlog between neighbors. It's kind of similar like to water flowing through a network of pipes through pressure gradients. For example, here we have 2 nodes, and each node maintains a queue of the payments to a destination. And it will pick the commodity in the terms of back pressure routing. It's a payment that with a maximum backlog. For example, here we have node A and B, each have balance 40, 60, and these are the queue lengths. And each node will compare, and node A will send a blue over link A to B because it observes the largest back pressure log. And similarly, node B will send the green commodities over link B to A because that has a maximum back pressure log from B's point of view. So yeah, this is the first principle, follow the congestion gradients. And the second principle of DBRs is to keep the channels balanced as possible, because this is the key to make the network as connected and have the nice forwarding properties. So DBR takes the channel balance into consideration. Initially, it has tunable parameters to adjust the channel balance and the differential backlog together. For example, here in the same example, we notice that here we changed the balance here from initially it was 40, 60. Now see the node A and B has a balance of 90 and 10. So node A will send a blue commodity over link A and B as well. But node B, since here B already observe a significant imbalance of the channel, then it will wait. It will wait until the backlog gets larger or the channel get more imbalanced. So all these parameters that can be tuned so that you can, so that the routing algorithm can choose a sweet spot between the latency and the channel balance. Now there's some formal math model of it, and actually, so the detailed formalization and implementation of this routing algorithm is implemented by the other team member, Qin Kai of Celer Network, who couldn't come due to some visa issues. So we have these different notations like capacity of link from I to J and the total deposit of the bidirectional payment channel, the total amount of tokens that should be delivered to a destination, and then the amount of tokens that are allowed to be sent over link I to J. So we can construct the data queue through these equations. Since time, we may not have the exact time to continue with the details, but it's basically to how many value you want to transfer through it, but it's still waiting. And we can also define the channel imbalance, basically the difference between the 2 directions. And with this data queue, which is corresponding to the differential backlog we talked before, and this channel balance. So we can define the congestion plus imbalance weight for the link I to J to the destination K as it follows, Wij kt. And we have, see here, we have a beta parameter that you can adjust the importance of channel balancing. And the DBR algorithm is actually surprisingly simple. So at each time slot, the node only needs to exchange its information with its neighbors and calculate these CPI weights. And then for each link, it will calculate the best payment flow to transmit over this link through the argmax computation and find the flow that can maximum this congestion plus imbalance weight. So that's it. And I want to have like a quick overview of the performance guarantee of these algorithms. So we define the network payment that is stable if the total desk queue, like the payment waiting in each intermediate node that are waiting to be transferred, remains bounded for any time, for any given time. Then we call it the network is stable. And then we define the network is balanced if, say, for the total of the network, the payment from one direction to another and the reverse direction are roughly the same. And then we actually have a net properties that for any global payment arrival process, some like payment arrival vectors, the DBR algorithm can always keep the network stable and balanced as long as there is an existing algorithm that is able to do so. This algorithm could be an Oracle algorithm that may not be possible to be implemented in a distributed way. But the DBR distributed algorithm can achieve such nice properties. And in our white paper, we have the proof, which is based on Lyapunov drift analysis. If you are interested, you can check it out for details. So DBR has this nice properties. First is provably optimal throughput, which means that it can support all payment patterns within the theoretical throughput region. And it has transparent channel balancing, because the channel balancing is embedded in the routing process. You do not need to need any out-of-band communication. And it is fully decentralized because each node only talks to its neighbors. And of course, it is failure resistance because each node can quickly detect and adapt to unresponsive node because by detecting the queue buildup. So this is some simulation results. It is it is a network with 77 nodes and with 254 bidirectional payment channel. Because we are injecting a large amount of random data, try to maximize the channel utilization. And we can see that once the payment volumes goes up, the traditional routing algorithms based on shortest path routing may perform really bad due to it needs to continuously reconverge, and it can never reconverge due to our based on our simulation results. And we can see that the channel utilization in our protocol can be very high. This channel utilization means that how many value you can transfer compared to the total deposit in this channel. This is a very important metric in payment networks because we all know that this liquidity deposit, it is one of the main costs for like a payment service provider to run a payment business. So in conclusion, I want to re-emphasize that off-chain payment network, it actually has fundamentally new challenges. It's because the link model is completely different from the data network. So we need to think beyond the conventional routing protocols that people have been studied for decades for the wired data networks. So Celer Network proposed a new perspective with optimal throughput, transparent channel balancing, fully decentralized, failure resilience, and privacy preserving. Of course, this is not the end of this work. We all know that to make a nice research work go to production, there are a lot of corner cases, stuffs we need to deal with, and we are doing active research to further improve this algorithm. Thank you very much.
Okay, we have time for one question. I'll give it to Pedro. I'm sorry. I'll give it to Pedro.
Hello, nice talk and nice work. So in your last slide, actually, you mentioned that you have privacy-preserving routing. So could you elaborate which notion of privacy do you achieve and to which degree you have it?
So our means of privacy is actually It's nothing like a specific contribution from our side. So basically, similar to speed murmur, we have this native multi-path routing, and as I said in one slide, we have the upper layer optional onion routing based to preserve the privacy, to hide the source and the destination to intermediate nodes.
Mm-hmm.
Yeah.
But so do you have any privacy analysis with respect to a privacy definition, or you just carry over the results that are out there?
We do not have specific analysis to privacy routing because it's just reusing the existing well-studied techniques such as onion routing, this stuff. Yeah, thanks.
Okay, awesome. So one more round of applause for him. Yes, good job.